Hi everyone! So let's make a review about Chapter 7. So on our course website, you can see there is a final review notes. So click that and then you see this. Okay, so this is the review notes for the whole semester, and right now we just need to look at Chapter 7. So chapter 7, we talk about integration techniques. Okay, and let's see. So 7.1, we talk about integration by parts. Okay. All right. Okay. So we talk about integration by parts, and the integration by parts formula is integral of u dv equals uv minus integral of v du. I hope you can remember this. Okay, so when do we use integration by parts? Remember, we don't have product rule or quotient rule for integrals. Okay, so when you see some products, actually there are three special kinds of products we are able to use integration by parts to solve the integrals. Okay, but like some other products, you might be able to use U substitution to solve it. Okay, so the first type is when we have power of x times exponential function, or power of x times sine and cosine. Okay, and here remember, we always let u be something we can differentiate and make the problem easier. So, and that's why we let u be x to the a, the power of x, okay? Because when we differentiate, we have the power of x actually decrease by 1, okay? The problem is easier. But if you let u be exponential function, sine or cosine, you realize when you differentiate, it's still the same difficulty, right? Derivative of exponential function is still exponential function. Derivative of sine is cosine. Derivative of cosine is sine. So that's why the first type, when we see a product of powers of x times exponential function or sine and cosine, you let u to be the power function, and then dv is the rest. Okay. The second type, when we have the power function times the inverse function. So I call them inverse function because ln of x is the inverse function for exponential function. Arcsine, arctangent, they are the inverse function for the trig function, right? In this case, we let u be something we can differentiate. So for all of this inverse function, we can only differentiate. We don't know how to find the integral of that. So we have to let u be their inverse function. Okay? And then the rest is going to be dv. The third type is when we have exponential products of exponential function and sine and cosine. In this case, you can let u be the exponential function, or you can let u be the sine or cosine. It doesn't matter. It will be the same difficulty. Okay, so when you start with exponential function times sine, when you do integration by parts once, you actually get the exponential function times cosine. So when you do the integration by parts second times, it will get this guy back. And then do you remember we have the integral and then equals something plus, and you can see the integral again. So what do? You move the integral to the left so you can combine. It's like, oh, when you have y equals 2 plus 3y, you move this to the left, you get minus 2y, and then you can solve for y. Okay, so that is 7.1. How about 7.2, the trig integrals? Okay, so we learned three types of trig integrals. The first type is the powers of sine and cosine. Okay, so we have three cases. First case, when the power of sine is odd. So what do? Do you remember? We split one of the factor at the end. Okay, and then you can, because the remaining factors of sine x is going to be even power. So because it's even, you can use the trig identities that sine squared plus cosine squared is 1. So sine squared is 1 minus cosine squared. So you can change the rest in terms of cosine. Okay, then we let u be cosine of x, then du is minus sine x dx. Okay, do you remember the song? Okay, I give you the tail of the animal. You can guess who's the animal. Okay, so you can see the tail is sine x dx, then you know your u should be cosine. So that's why you know you're going to change this guy in terms of cosine. Okay, next. If the power of cosine is odd, similarly, you split one of the cosine at the end and change the rest in terms of sine. Okay, because then you let u be sine, your du, your tail, is going to be cosine x dx. Okay, if both of them are even, so sine to the even power and cosine to the even power, we use double angle formula to decrease the degree and double the angle. Okay, what are the double angle formula? So here is sine 2x, this is cosine 2x. But what you're actually going to use is the one that cosine square is 1/2 plus 1/2 cosine 2x, and sine square is 1/2 minus 1/2 cosine 2x. So keep this in mind. Okay. All right. So next, we're gonna have integral of products of tangent and secant. We also have 3 cases. First case, when the power of tangent is odd. Okay, then what do? You want to have the tail, tangent, secant at the end. Sometimes you don't have secant, then you're gonna borrow it from the bank. How do you borrow it from the bank? You multiply by secant x, and you also multiply by, we don't use this notation. Okay, after you multiply by secant x, you also divide it by secant x. So then that is how you borrow it from the bank. Okay, and then secant, tangent secant is the derivative of what? Remember, I gave you the tail and you tell me what is the animal. The animal is secant x, right? So that's why you can change the rest in terms of secant. And when the power of secant is even, okay, in that case, you're going to split secant square at the end. Okay, so what is secant square is the derivative of what function? Yes, tangent. So that's why you're going to change the rest in terms of tangent. Then you let u be tangent, du be secant x dx, secant square dx. The third case is when the power of tangent is even and the power of secant is odd. So in this case, it's hard. It requires some tricks, and it really depends on the problem. Okay, but you won't see this case in the exams. All right. And also, I hope you can remember the integral of tangent x and the integral of secant x. If you don't remember, it's okay. You can always derive it. Okay, remember tangent, how to integrate tangent. You can put secant tangent, and then you can put 1 over secant in the front. And then you can use the u substitution. Okay, next. The third type is when we have integral of sine alpha x times sine beta x, or cosine alpha x times cosine beta x, or sine alpha x times cosine beta x. So in this case, if I ask you a problem like this, the formula will be given. Okay, so what do is use the formula, turn the products into sum or difference, and then you can just integrate them easily using the formula of sine and cosine. All right, so that is 7.2 trig integrals. Next, we're going to have 7.3, the hardest section in Calculus 2, trig substitution. Okay, we only have 3 kinds of trig substitution. They are sine, tangent, and secant. So when you see square roots of a squared plus x squared in your integral, sometimes you might not see like exactly the square roots of a squared plus x squared. Sometimes you may see, for example, maybe a squared plus x squared to the 3/2. Okay, like that. In this case, you always think about the trig substitution, x equals to a tangent x, okay? And then the square roots of a squared plus x squared is going to be, who's the wife of tangent? Yeah, secant. So tangent and secant, they are a couple. Sine and cosine, they are a couple. So that's why here, after that, you know the x is going to be a derivative of tangent is what? Secant square d theta. Okay, and then you can put this in the integral and integrate. So after you're done, so this is a triangle. Okay, after you're done, you have the angle theta, and you want to plot the x back. So you draw the picture, you know tangent theta is x over a. Okay, so x is opposite over adjacent, so x over a. So you put x in the opposites, a in the adjacent. The hypotenuse is going to be square root of a squared plus x squared. Okay, and then next, when you see square roots of a squared minus x squared in your integral, you're going to let x to be a sine theta. Okay, and then the square root of a squared minus x squared is going to be, who's the wife of sine? That is cosine, right? So we're going to have this. And what is the derivative? What's dx? Dx is a derivative of sine is cosine theta d theta. All right. Last, and when you see the square roots of x squared minus a squared, you let x be a secant theta. And then the square root of x squared minus a squared is going to be a tangent theta. Remember, secant and tangent, they're a couple. And then dx is going to be a secant theta, tangent theta, d theta. Okay? So keep this in mind. And when you see these three kinds of integrals, you actually don't need to use a trig substitution. Okay, because we have the formula for it. The formula of 1 over x squared plus a squared is 1 over a tangent of x over a. Okay, and then integral of 1 over square root of a squared minus x squared is x sine of x over a. So remember here, the x sign is special because you don't have 1 over a in front. And then when you have integral of 1 over x square root of x squared minus a squared, that is 1 over a secant of x over a. So please be careful. Don't forget your baby dx and the d theta, okay? So your dx is not only just d theta, it could be, you can see, it could be a secant squared d theta, it could be a cosine d theta, it could be a secant tangent, and then d theta. So that's why don't forget your baby. If you forget your baby here, well, you have the wrong integral and then you cannot continue. Okay, so that is 7.3 trig substitution. And then 7.4 partial fraction. Okay, so when we are given a rational function, the first step is we check whether the rational function is proper. If it's proper, then we go to the next step. If it's not proper, you use long division so that you can have a polynomial. Polynomial plus the remainder over the divisor. Okay, so polynomial, you can actually integrate it, right? For the remainder over divisor, this is actually a proper fraction, and then you can go to step 2. Okay, so Step 2, you're gonna look at the denominator, factor the denominator completely, and then look at each factor. If you get distinct linear factor, you're gonna set it up like this. If you get repeated linear factor, you're gonna set it like this. So if your factor the multiplicity is like x to the r, then you first put the factor and then you keep increase the multiplicity until you keep increasing the powers until you reach the multiplicity. But in this case, the numerators, when you set it up, they are constant, okay? And the third case, when we have irreducible quadratic. Okay, what is irreducible quadratic? Quadratic means it's degree 2. How do we know it's irreducible? Well, you look at the discriminant, okay? B squared minus 4ac. So this is the guy inside the square root when you try to solve x, okay? So if the discriminant is negative, then it means you're gonna have no real roots, okay? So the quadratic factor cannot be decomposed into a product of two linear factors. So in this case, your setup is you put, because it's simple, proper fraction. Simple means the denominator you only have one kind of factor. Proper means the numerator, the degree of the numerator is less than the degree of the denominator. Because the denominator we have degree 2, the numerator must have degree 1. So the general form for degree 1 function is ax plus b. Okay, so when we have case 4, the repeated irreducible quadratic, so you won't need to integrate this guy, but when you set it up, you will see it. Okay, so I'm gonna ask you two type of function. One type is I give you a complicated fractions, and then you're gonna ask you to set it up, how to decompose into simple proper fractions. Then you're gonna expect what? The ABC sign, A, B, C, D, E, F, G, H, I, okay? And then the second type is I actually ask you to solve the integrals. So in this case, you will see at most 4 constants, okay? All right, so then 7.7 is improper integrals. Okay, improper integrals, we have two types. When x goes to infinity, we have infinite interval. Okay, the second type is when the y goes to infinity, we have unbounded integrand. Okay, so first of all, you let t be the improper value. In this case, the improper value is infinity, right? And then you compute the integral. For unbounded integrand, you figure out what is the improper value. In this case, which value is undefined? You can see this function is not defined when the denominator is 0. So that is x is 0. Okay, so that's why you replace 0 by t, but you also need to figure out its left side limit or right side limit. So then you look at the interval from 0 to 1, you're approaching 0 from the right. So that's why you have the right-sided limit. Okay, and we also have the p-test. What is the p-test? P-test, when we have the integral 1 to infinity of 1 over x to the p, okay, this integral converges for p greater than 1. It diverges for p less than equal to 1. Okay, remember that. So you can imagine that when p equals to 1, this is like this guy is actually like the boundary. The area here is gonna be infinite. So the integral diverges. Okay, what do you know what happened when p is less than 1? So when p is less than 1, your integral is actually taller. So 1 over xp is actually bigger when x greater than 1 is actually bigger than 1 over x. So that's why while the blue area should be bigger than the red area, so it also is infinite, it diverges. Okay, but when p is greater than 1, what happened? So when p is greater than 1, what happened is your integral is going to be smaller than 1 over x. So that's why we have converges here. The area is finite. Okay, so that is the p-test. And also very important is the p-test works for integral from a number. The number is not necessary to be 1. It could be any big number, let's say n. And so the p-test is work for the integral from n to infinity. Okay? It doesn't work for example, 0 to 1 over x cubed dx. So it doesn't work for here. So you're going to be very, very careful. Okay? And then we have the comparison test. Remember big guy and small guy? Okay, so we know G is the big guy and F is the small guy. If the big guy converge means like finite. If the big guy's area is finite, then the small guy, the area is also finite. If the small guy, the area is infinite, then the big guy, the area is also infinite. Okay? So just use your common sense or draw pictures, then you can figure out that. And when do we use comparison tests? Well, we use comparison tests when you are not able to integrate the integral. Okay, so you can look at our handouts from 7.7. There are some integrals that we are not able to integrate, but you can look at the dominant terms. Okay, if they're rational functions, the dominant terms is the terms with the highest power. Okay, when x goes to infinity, the dominant term is dominant. So you can look at the dominant terms and figure out what is the 1 over x to p, what's the p value, then you can use comparison test to relate to this integral, and then you can make conclusion about that. Okay. Last, session 7.8, we talk about separable differential equation. Okay, what you do is you first express the right hand side as a product of function of y and function of x, and then you want to move the y to the left and then keep the x to the right. Okay, so then after you do that, you can integrate both sides respectively, and you have a constancy. If you have initial condition, then you can plug in your initial condition and solve for c and then get the solution. Sometimes if the problem asks you to solve the solution explicitly, then you need to solve for y. Okay, but if the problem asks you no need to solve the solution explicitly, then you can just keep it like that. All right, so that is chapter 7. When you have questions, feel free to email me or ask me during the online office hours. All right, bye.